For the first time in history, scientists face the unthinkable. The cosmos might not be orderly or unique. Instead, it could be a fractured, indifferent labyrinth where meaning is lost and existence itself is a cosmic accident. This chilling possibility haunts the edges of physics, threatening to unravel everything we thought we knew about reality, life, and our place in the universe. What lies beyond our universe's fragile horizon? And if countless others exist, will we ever escape the prison of our singular reality? Or are we doomed to forever be lost, alone in a cold, infinite multiverse? Between the cold silence of galaxies and the vast emptiness where even light takes millions of years to travel, there is a terrifying possibility no one dares to fully face. Scientists, the greatest minds of our time, whisper in fear, what if our entire universe is nothing but one fragile bubble among an endless sea of others? A cosmic ocean so vast, so incomprehensibly immense, that it swallows certainty itself. If true, the laws of physics we depend on, gravity, time, the speed of light, are not universal. They are local, fragile rules, confined to this bubble we call reality. Outside this thin veil, everything we understand might collapse into chaos. Imagine a cold, infinite void filled with infinite worlds, some eerily like ours, others alien beyond imagination. Realities where time fractures, where cause and effect vanish, where light does not exist, or where existence is pure torment. The terrifying truth is that somewhere, these universes are not just theories, they may be real. And if they are, every possibility, every nightmare, every version of you exists somewhere in that endless expanse. In the silent gulf between galaxies, where even starlight takes millions of years to cross the void, a lone observer drifts around them. The universe seems endless, but perhaps it is not. Perhaps this vastness is only the surface of something far greater. The stars shimmer like distant embers on a cold night, but beyond them, beyond the reach of any telescope, there may be other fires, other skies, other laws of nature entirely. Our universe, with its galaxies, its dark matter, its relentless expansion, may be no more than a single droplet in a boundless cosmic ocean. An ocean where each droplet is a separate reality, sealed off, unseen, yet infinite. Imagine a hall of mirrors with reflections that are not copies, but entirely new worlds. Worlds where time flows in spirals, where gravity repels instead of pulls, where light is not the fastest thing, or where there is no light at all. Somewhere, beyond the curtain of space-time, those realities might unfold untouched, unreachable. If they exist, they're not simply curiosities. They challenge the deepest foundations of science, because if there are other universes, then the rules that shape ours are not unique. They are local, accidental, perhaps even fragile. And so the question rises like a shadow on the edge of thought. What lies beyond our cosmic horizon? If our universe is just one among countless others, then our story, the story of life, of time, of everything we know, is not the only story. Somewhere, there may be others, written in entirely different alphabets of reality. Long before the language of mathematics carved the laws of nature into equations, the human mind was already reaching for the edges of reality in the philosophies of ancient Greece. The atomists Leucippus and Democritus imagined an infinite void, populated not by a single cosmos, but by countless worlds, each born from the ceaseless motion of indivisible particles. They spoke of universes colliding and separating, of worlds where suns might rise and fall on lands we would never see. To them, nature's creativity was boundless, and space was an eternal stage for its infinite performances. In the hymns of Hindu cosmology, the universe was not singular, but one in an eternal cycle of births and dissolutions, like breath drawn and released by a cosmic being. Kalpa's unimaginably long epochs would pass as universes emerged from the cosmic ocean, only to dissolve back into it, replaced by others. The idea of many worlds was not speculation. It was simply the natural order of things. In the Buddhist vision of endless worlds, universes bloomed like flowers across an infinite field, each with its own sky, its own measure of time, its own arrangement of elements. None was privileged. As the true reality, they were all expressions of a deeper, incomprehensible whole. For millennia, these visions lived in the realm of story and philosophy. But as science matured and its tools became sharper, ideas once seen as metaphysical poetry began to find strange echoes in mathematics and observation. In the mid-20th century, physics faced a troubling mystery. The quantum world refused to behave like the predictable clockwork of Newton's cosmos. Subatomic particles acted as though reality were made not of certainty, but of probabilities. This was not mere unpredictability. It was as though reality itself only chose its form when observed. In 1957, a young physicist named Hugh Everett proposed a radical answer to the many worlds interpretation of quantum mechanics. In his view, every quantum event, every unpredictable flicker of reality caused the universe to split, branching into separate histories. In one universe, a particle spins left. In another, it spins right. In one, a star collapses into a black hole. In another, it burns for billions more years. Most physicists of the time dismissed Everett's idea as a bizarre and unnecessary extravagance. But it planted a seed that the universe we inhabit might not be alone, the one among an endless branching of realities, each as real as our own, yet forever inaccessible. Everett's theory remained on the fringe, yet it lingered a shadow in the corners of physics, waiting for other ideas to draw it into the light. 2 decades later, the focus of cosmology shifted to the earliest moments of the universe. Observations revealed something puzzling. The cosmos was remarkably uniform in temperature and structure, even across vast regions that should never have been in contact according to the speed of light. This mystery, the horizon problem, demanded an explanation. In 1980, physicist Guth proposed cosmic inflation, the idea that, in the first fraction of a second after the Big Bang, the universe expanded exponentially faster than the speed of light. This rapid expansion stretched space itself, ironing out irregularities and explaining the uniformity we see today. But inflation also carried an extraordinary implication. If the inflationary process could occur once, it might occur repeatedly in different places, at different times. Andrei. Linde took this further with his chaotic inflation model. In it, inflation never truly ends. It simply slows in some regions while continuing in others. Each region where it stops becomes a bubble universe. While inflation continues to create more bubbles endlessly, these bubbles would be separate, each with its own local laws of physics, and we might inhabit just one among countless others, scattered across a multiverse without boundaries at first. These ideas were treated as mathematical possibilities, interesting but unreachable by evidence. Yet, as cosmology entered the age of precision measurement, hints began to surface that could not be ignored. Satellites mapping the cosmic microwave. Background: CMB. The ancient light released when the universe was only 380,000 years old revealed a pattern of faint temperature fluctuations. Most were expected, the seeds of galaxies yet to form, but among them lay something strange. A vast, unusually cold region, hundreds of millions of light years across, standing out against the otherwise smooth backdrop of space. This cold spot was first identified by NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later confirmed with greater precision by the European Space Agency's Planck satellite. Its nature remains debated. Some suggest it is caused by an enormous cosmic void, a vast region of space with fewer galaxies than average, allowing light to lose more energy as it travels through. Others have whispered a more exotic possibility, that the cold spot could be the faint scar left by a collision between our bubble universe and another in the deep past. For the first time, the multiverse stepped from the realm of pure speculation into the thin borderland where theory meets observation. This was not proof far from it, but it was enough to shift the question. No longer was the multiverse an idea to be idly entertained in late-night conversations among theorists. Now, it had a foothold in the faint afterglow of creation itself, and so, a small but growing number of scientists began to wonder, what if the anomalies in our sky are not flaws in our measurements, but whispers from beyond our universe's horizon? What if the afterglow of the Big Bang carries, hidden in its mottled light, the fingerprints of other worlds, worlds forever out of reach, yet close enough to have brushed against our own in the darkness before history began? The more they studied, the more they realized. To answer this would mean answering one of the deepest questions in science, whether our universe is a singular masterpiece, or just one frame in an infinite reel of cosmic film. In the great halls of science, where the laws of nature are written like sacred scripture, there has always been an unspoken assumption that reality is singular, that there is one cosmos, one set of rules, one stage on which every star, galaxy, and living being performs its brief act before fading into history. The idea of a multiverse was once considered a trespass into philosophy, a speculation too wild, too ungrounded, too impossible to test. To many physicists, it belonged not to the realm of equations, but to the realm of dreams. Science, after all, is built on the principle of falsifiability, the idea that a claim must be testable, or it does not belong to science at all. And how, they asked, could one ever test the existence of universes beyond our own? If no signal can cross the void between them, no telescope can see their light, and no particle can bridge the gulf, then the multiverse seemed forever beyond the reach of experiment. For decades, this was the consensus. One universe was enough. It was a comforting thought, the belief that the laws of physics we discover here are the same everywhere. Immutable and eternal, Einstein's general relativity gave this picture mathematical strength. Space-time as a single, self-contained fabric, bending and curving under the weight of matter, but never branching into other realms. But then, the equations began whispering otherwise. From the strange predictions of cosmic inflation, a picture emerged of a universe that might not have been a singular event, but part of a chain reaction, a cosmic field that could spawn bubble after bubble of space-time, each sealed off from the others by distances so vast that no information could ever pass between them. And in each bubble, the conditions at birth could be radically different. Different constants, different forces, different histories. This was not just a new theory. It was a fracture in the very idea of a universal reality. If these other universes truly exist, then our laws of physics are not inevitable. They are just one of countless possible arrangements. The speed of light, the strength of gravity, the masses of fundamental particles. Here they are precisely tuned to allow stars, planets, and life to form. Elsewhere, perhaps the laws are chaotic, sterile, incapable of sustaining even a single atom of stability. And in others still, they might give rise to unimaginable forms of matter and consciousness. The implications were dizzying. Physics, which had always sought the one true description of nature, now faced a disturbing possibility. There may be no single description at all. The dream of a final theory, a neat, complete equation, explaining everything, could dissolve into a library of infinite possibilities, each equally real in its own domain. For many scientists, this was a philosophical earthquake. How does one practice science in a reality where anything that can happen has happened somewhere? If every experiment's outcome occurs in some branch of reality, then probability itself becomes a strange illusion, and the meaning of prediction begins to blur. In such a cosmos, evidence becomes a local phenomenon, not a universal truth, even. Einstein's elegant vision was caught in the crossfire. His general relativity describes a universe that is self-contained, a smooth continuum that begins and ends as one whole. But the multiverse threatens this vision with something far stranger. A cosmos that is not a single surface, but a garden of endlessly budding spacetimes, each detached, yet born from the same quantum soil. Where Einstein saw one great river of spacetime flowing from the Big Bang, modern theories hint at a delta, an infinite branching, each tributary, flowing into its own ocean. And then there is the most unsettling consequence of all. If infinite universes exist, then infinite versions of you also exist. There are worlds where you are living a completely different life, worlds where you made different choices, worlds where you never existed at all, and stranger still, worlds where every possible version of you is real. The triumphant you, the defeated you, the you who never left home, the you who never learned your own name. It is a thought both intoxicating and terrifying. Because in the multiverse, reality becomes not a single narrative, but a sea of every narrative that can be imagined and countless more that cannot. Identity itself becomes a fragile concept, a local arrangement of atoms and memories in one branch of a cosmic infinity. In the quiet offices of universities and research institutes, this idea has caused more than discomfort. It has forced a re-examination of what science is meant to do. For centuries, the goal was to uncover the one truth of the cosmos, but if the multiverse is real, then truth may not be singular. It may be a mosaic of infinities, each as valid and self-consistent as our own. Some physicists have embraced this possibility, seeing in it a grander vision of existence, one in which the universe is not limited by our imagination and reality is endlessly creative. Others reject it, holding fast to the belief that without evidence, the multiverse remains a philosophical ghost haunting the corridors of science, but never stepping fully into the light. And so, the debate continues between the comfort of a single, orderly universe and the dizzying freedom of infinite worlds, between the precision of Einstein's equations and the wild branching of cosmic inflation, between the desire for certainty and the acceptance of an unbounded reality. Somewhere, perhaps in another universe, the answer is already known. But here, in this one, the question remains lingering like a distant echo, a ripple from beyond the edge of our cosmic horizon. The further humanity peers into the cosmic night, the more intricate the map becomes. The cosmic microwave background, the faint afterglow of the Big Bang, remains the oldest light we can see. It is not uniform. It shimmers with delicate variations in temperature and density, each a frozen echo of sound waves in the infant universe. Early missions like COBIT, launched in 1989, gave us the first coarse image of this primordial light, a mottled pattern, like the surface of ancient parchment. Then came WMAP in 2001, sharpening the image into a finer tapestry. And finally, the Planck satellite, launched by the European Space Agency in 2009, delivered the most exquisite map yet, its measurements so precise that even a whisper of anomaly could no longer hide. In the noise, scientists turned to these maps with a new question. Could they hold scars of a greater story? In the inflationary model, our universe began as a rapidly expanding bubble in a larger, still-growing cosmic foam. If other bubbles formed close enough, their collisions could leave imprints, faint circular patterns, temperature gradients, or distortions in the CMB. Planck's data revealed subtle curiosities. A large, unusually cold region, the so-called cold spot, spans 1,500 million light-years across the southern hemisphere of the CMB map. Its temperature is ever so slightly lower than expected, not enough to defy physics outright, but enough to invite whispers. Some simulations suggest such a feature could arise naturally from random fluctuations. Others propose something more, the aftershock of a collision with another universe, long before galaxies were born. But the CMB is not the only map we have. Here, the Sloan Digital Sky Survey steps into the frame. For 2 decades, its telescopes have scanned the sky, cataloging the positions and redshifts of millions of galaxies. From these data emerges a cosmic web, vast filaments of matter spanning hundreds of millions of light years, with dark voids yawning in between, the shapes, alignments, and symmetries of this web tell us about the curvature and topology of space itself. If the universe is infinite, the web should extend without pattern or boundary. But if the universe has a finite, folded shape like the surface of a higher dimensional torus, certain patterns should repeat, like a cosmic wallpaper. So far, no perfect repetitions have been found. Yet, strange alignments in the distribution of galaxies' preferred directions, where none should exist, remain unexplained. DESI, the dark energy spectroscopic instrument, now continues this work with unprecedented precision. It measures the light from tens of millions of galaxies and quasars, mapping not just where matter is, but how it has flowed and stretched over cosmic time. Small deviations in this flow could hint at distortions from outside our universe, a gravitational tug from an unseen neighbor in the multiverse. Meanwhile, theorists have taken to simulations universes born and destroyed inside the circuits of supercomputers and many models of cosmic inflation. The quantum fields that drove our universe's birth are unstable, cascading into countless variations. In some, inflation stops in one region while continuing in another, producing a foam of bubble universes. Each bubble may have its own constants of nature, its own particles, even its own number of dimensions. Some simulations predict that collisions between these bubbles are inevitable, violent, yet strangely silent. Since no sound can travel between universes, the evidence, if it survives, would be subtle, a ring-like temperature shift in the CMB, or an unlikely statistical alignment in galaxy clusters. Detecting such a signature is a challenge that has occupied entire careers. And beyond cosmology, particle physics joins the investigation. At the Large Hadron Collider, protons smash together at energies approaching those of the universe's first moments. Physicists watch for the faintest deviation from the standard model, a sign of symmetry breaking that could reveal the true nature of the vacuum itself. In quantum field theory, the vacuum is not nothing. It is a seething field of energy with its own state. Some theories propose that our vacuum is only one of many possible configurations, each with its own laws of physics. If so, the Big Bang may have been not the start of everything, but a transition, a shift from one vacuum state to another, perhaps triggered by a fluctuation in a larger multiversal landscape. Here too, anomalies lurk. Experiments have found no conclusive evidence for extra dimensions or exotic particles, but certain measurements, tiny tensions in the mass of the W boson, or unexpected behavior in one-spin experiments hint that our understanding is incomplete. If confirmed, such cracks in the standard model could open a door to physics beyond our universe's boundaries. And still, the strangest clues remain the most disputed. The low multipole alignments in the CMB, large-scale patterns that appear too straight, have persisted across missions. From WMAP to Planck, some physicists call it the axis of evil, a playful yet provocative name for something that should not exist if the universe is truly random and isotropic. Others dismiss it as statistical noise, yet its persistence gnaws at the edges of certainty. Even galaxy surveys have found curious signals, vast voids larger than models predict, alignments in quasar polarization over billions of light years, hints of structure where none should remain from the chaotic birth of space. Each discovery comes wrapped in caution, for the cosmos is adept at producing illusions, but each also keeps the door just slightly ajar. The deeper the measurements go, the more reality resembles a riddle written in patterns of light and shadow. It may be that the anomalies are nothing more than the playful chaos of a universe too large for our instruments. Or it may be that they are footprints faint, distorted, and half buried left by other universes that brushed against our own. If that is the case, then the maps we hold, the CMB surveys, the galaxy charts, the data from colliders are not just tools of measurement. They are fragments of a larger atlas, one we cannot yet read in full. Each new observation is a pixel, slowly revealing an image far greater than the frame we thought contained it. And so the investigation deepens into the cold afterglow of the Big Bang, into the tangled web of galaxies, into the subatomic fabric of the vacuum itself. Every anomaly, every unexplained pattern, every whisper in the data is weighed, tested and retested. The answers remain elusive, but the questions have never been clearer. What lies beyond the limits of our map? And is our universe only one small continent in a vast, unseen archipelago of worlds? In the stillness of deep space, where light has traveled for billions of years only to fade into a ghostly whisper, a question stirs: is our universe all that exists? Or is it merely a single drop in an endless, cosmic ocean, one bubble adrift in an eternal sea of creation? Modern cosmology offers a theory as audacious as it is unsettling: eternal inflation. In the earliest fractions of a second after the Big Bang, the universe did not simply expand, it ballooned, a violent, incomprehensible surge of space itself, driven by a mysterious energy locked within the quantum fabric. And in this model, that expansion never truly stopped, while our local bubble slowed, cooled, and formed galaxies. Other regions kept inflating, faster than light, beyond reach, beyond time. Each bubble becoming its own universe, sealed away by distances no signal could ever cross. Some theorists suggest that these bubbles are not perfect spheres adrift in a void, but waves in a cosmic foam of frothing, infinite sea of universes being born and dying in a process without end. And if these bubbles sometimes collide, the impact might leave scars. Subtle ripples imprinted into the cosmic microwave background, the ancient afterglow of the Big Bang. Astronomers have searched for such marks: faint circles, cold spots, asymmetric patterns. Some claims have emerged, tantalizing but inconclusive. The universe guards its secrets well. But the implications go deeper. Beyond inflation lies another idea born not from astronomy, but from the mathematics of string theory. Here, reality is woven from vibrating strands of energy, curled through dimensions far smaller than an atom. And the equations do not give us one universe. They give us a staggering 10,500 possible universes, each with its own laws, its own constants, its own dimensional structure. Physicists call this the string landscape, a realm so vast that compared to it, our observable universe is smaller than a single grain of sand in all the deserts of Earth. It is here that the problem of fine-tuning takes center stage. Our universe's physical constants, the strength of gravity, the mass of the electron, the speed of light are balanced with uncanny precision. Alter them even slightly, and atoms would never form. Stars would never ignite. Life would never arise. Why should they be so perfect? Why should the universe permit life at all? In the multiverse, one answer emerges. Most universes are barren, chaotic, lifeless. But in the vast lottery of possibilities, a few by pure chance have the right conditions, and we, inevitably, find ourselves in one of them because we could not exist in any other. Yet this explanation carries a strange weight. If there are infinite universes, is life inevitable? Or does its inevitability strip it of meaning? Does the multiverse make us special, or does it make us nothing at all? These are not questions physics can easily answer. They belong to philosophy, to the human spirit, to that quiet place in the mind where wonder and dread meet. Some scientists, restless with even these possibilities, venture further into speculation. What if black holes are not cosmic dead ends, but gateways? A collapsing star creates a singularity, a point where our physics shatters. Inside, time and space as we know them cease to exist. Some propose that, beyond that veil, a new universe could be born, a baby cosmos, expanding in its own direction. Of time, forever sealed from its parent. In this view, universes reproduce. Each black hole becomes a cosmic womb, spawning new realities with slightly altered physical laws over unimaginable eons. The multiverse might evolve universes that make more black holes, giving rise to more offspring, shaping the distribution of laws themselves. Others reach for the quantum, those restless, flickering fluctuations that never stop. Even in a perfect vacuum, could such fluctuations, under rare conditions, inflate into entire universes? Could reality be bubbling with tiny newborn worlds, forever branching away from ours? The deeper science peers into the nature of existence. The more it seems the universe is not a single, coherent story, but a library. A library where each book tells a different version of reality, some short and violent, some long and luminous, most unreadable. And here we are, a self-aware chapter within one of them, trying to understand not just the plot, but the shelves that hold the books themselves. Yet the mystery remains. If there is an infinite number of universes, then somewhere there is another where you are reading these same words. But the sky above you holds 3 suns, another where life never evolved, and another where everything is the same except for one atom, in one cell, in one forgotten ocean, eternal inflation, bubble collisions, a landscape of impossible variety, black holes as mothers of worlds, quantum whispers becoming cosmic roars. Each theory widens the horizon, and with it, the unsettling realization that perhaps we will never see beyond the glass walls of our own cosmic bubble. We might map every galaxy, measure every particle, and still be no closer to touching the universe next door. The mystery only deepens. And yet the human mind persists. Even here, staring into the infinite, it asks not just how such realities could exist, but why they should. The night sky is not a silent ocean. It is a restless sea of possibilities. And every glimmer we see may be only the surface of a far deeper reality. For centuries, humans have stared upward and imagined other worlds. But in recent decades, a new wave of bold theories has emerged, not of other planets, but of other universes. Each is a bridge between known science and the edge of imagination. Each dares to explain how our cosmos might be only one among countless others. Eternal inflation theory. In the early 1980s, Guth and Andrei Linde proposed that the Big Bang was not a singular, isolated event, but a fragment of something far grander. Inflation, the explosive expansion of the universe in its first fraction of a second, may not have happened just once. In some models, the process never truly stops. Like bubbles endlessly forming in a boiling pot, inflation might give birth to pocket universes forever, each sealed off from the others, each with its own beginning, its own cosmic story. In this vision, our universe is one bubble in an eternal cosmic foam. Some bubbles may be like ours, others may be unimaginably alien. Their physical laws bent in ways we cannot survive or even conceive. The mathematics is compelling, and inflation already explains much about our own cosmos, its flatness, its large-scale uniformity, yet its eternal form may remain forever hidden from direct observation, sealed behind the uncrossable walls between universes. The string theory landscape, at the smallest scales. Reality may not be built of particles at all, but of tiny vibrating strings, each oscillating in hidden dimensions curled far beyond our perception. String theory, still unproven, contains within it a staggering implication, the so-called landscape of solutions. For every way these extra dimensions could be shaped, a different universe could arise. Different shapes mean different constants of nature. The strength of gravity, the mass of an electron, even the number of forces. The variety is almost incomprehensible. Perhaps 10500, 10500, 10500 possible configurations. In such a landscape, our universe is simply one coordinate among an unfathomable expanse of possibilities. But here lies the dilemma. If everything is possible, what does it mean to explain this universe? Without a clear way to test the landscape, it remains a breathtaking idea, balanced on the edge of physics and philosophy. Many worlds' interpretation of quantum mechanics. In 1957, Hugh Everett proposed a radical solution to the strangest riddle. In physics quantum superposition, if a particle can exist in multiple states at once, and observation forces it into one outcome, what happens to the other possibilities? Everett's answer was shocking. They don't vanish. They unfold into parallel realities, each as real as our own. Every quantum event, every flip of a subatomic coin causes the universe to branch. Somewhere, another version of you exists, not as fiction, but as the inevitable consequence of quantum law. This idea needs no new physics, only a new way of interpreting it. Yet it is a theory forever beyond experimental confirmation, for these branching worlds, if they exist, remain sealed away from us. Cyclic or ekpyrotic universes. Roger Penrose's conformal cyclic cosmology envisions time not as a straight arrow, but as an endless loop. In this model, the universe is born, expands, and thins into a cold, empty expanse, and from that stillness, a new Big Bang emerges. The ancient Hindu and Buddhist cosmologies imagined endless cycles of creation and destruction, and now physics may offer its own echo of that vision. In Penrose's mathematics, the remote future of one universe becomes the beginning of the next, the boundaries between them blurred by the strange properties of space-time at its extremes. Hints may already be written in the cosmic microwave background faint. Circular patterns that some claim could be the shadows of black holes from a previous eon. The evidence is disputed, but the allure remains, that our universe has no ultimate beginning, no final end, only an eternal rhythm. Black hole cosmology. Nikodem Poplawski offers a striking thought. What if black holes are not just endings, but beginnings? General relativity predicts that inside a black hole's event horizon lies a singularity, a point of infinite density where known physics breaks. But quantum gravity may tell a different story. Instead of collapsing to nothing, matter could rebound in a big bounce, forming a new expanding spacetime. In this view, every black hole in our universe might be the seed of a baby universe beyond our reach. And our own Big Bang could have been the birth cry of a black hole in another cosmos. If true, the multiverse would not be scattered randomly, it would grow like a tree, each universe sprouting from the collapse of another, the mathematical universe. Hypothesis. Physicist Max Tegmark takes the boldest step of all. Perhaps the reason the universe is so mathematical is because it is mathematics. Every structure that can be defined mathematically, every consistent set of rules, exists as its own reality. Our cosmos, with its atoms and galaxies, is simply one solution in an infinite library of possible mathematical worlds. In this framework, existence is not a special privilege, it is inevitable. The price is unsettling. We are not unique. We are not even rare. We are simply one among all that can be. Strengths, weaknesses, and the weight of the unknown. Each of these theories reaches into the same darkness, and each shines a different light. Eternal inflation is rooted in tested cosmology, but hides its proof beyond any horizon. String theory offers elegance and unification, but drowns in an ocean of untestable possibilities. Many worlds makes no new predictions, yet it explains quantum reality without collapsing the wave function. Cyclic models promise no beginning, but struggle to match every observation. Of the early universe, Black hole cosmology reframes death as creation, but waits for a theory of quantum gravity to stand on. The mathematical universe embraces every possibility, and in doing so, risks explaining nothing at all. Yet perhaps these are not flaws, but signs of the frontier. For science at its edge is not a map, but a horizon, and beyond that horizon, there may be more than one sky in the quest to uncover whether our universe is truly alone. Humanity's most sensitive instruments now stand like sentinels at the edge of knowledge, listening, watching, and reaching for whispers from beyond our cosmic horizon. The search does not begin with the stars, but with the faintest fossil light in the cosmos, the cosmic microwave background. This ancient afterglow, born just 380,000 years after the Big Bang, carries within it a subtle polarization, tiny twists and alignments of light waves that may contain the fingerprints of other universes brushing against our own. In frozen silence at the South Pole, the Bicep Array peers upward through the clearest skies on Earth, searching for these patterns. From space, the Planck satellite's extensions refine the map, each pixel a time capsule from an era before galaxies, before atoms, before even light itself moved freely. Any anomaly, any unexpected ripple, could hint at a cosmic collision long before our own birth. The ghost of a boundary where two universes once touched. Yet, some signatures cannot be seen in light at all. They can only be felt in the trembling fabric of space-time itself. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, has already heard the final heartbeats of colliding black holes. In the decades ahead, its spacefaring counterpart, LISA, will drift in formation millions of kilometers apart, its arms of laser light stretched across the void. These gravitational wave observatories may, in principle, detect a shiver from far beyond our visible universe, the ripple of an unimaginable collision, perhaps from dimensions hidden to us. Closer to home, other missions chart the strange force that drives our universe apart. Dark energy, the Euclid mission, launched by ESA, and the Dark Energy Spectroscopic Instrument DESI, measure how galaxies are pulled, scattered, and accelerated by this mysterious pressure. If dark energy behaves differently in some corner of the cosmos, if its strength flickers or its nature shifts, it could be the first sign that our universe is only one bubble in a much larger sea. Beneath the surface of our planet, deep within colossal rings of magnets and detectors, sun accelerates particles to nearly the speed of light. Their collisions are flashes of the early universe, compressed into a fraction of a heartbeat. Here, scientists search for signs of extra dimensions, hidden layers of reality that may connect our universe to others. A particle suddenly vanishing into nothingness, a deviation in expected energies, could be a doorway glimpsed for the briefest instant before it seals again. Increasingly, these searches are guided not by human eyes alone, but by artificial intelligence. Neural networks consume petabytes of cosmic data, simulating billions of universes inside vast digital experiments. They compare, evolve, and discard possibilities in an endless cycle, learning to recognize the subtlest of patterns. In these machine-dreamed multiverses, we may find the key to identifying our own, or proof that ours is not unique. And still, the tools grow sharper. The James Webb Space Telescope, with its golden mirror unfolding in darkness, has already seen galaxies from the dawn of time and the years to come. Its follow-up missions will go further still. NASA's Raman Space Telescope will map the structure of the cosmos with unprecedented precision, while proposed CMB Stage 4 observatories aim to capture the microwave background in such detail that nothing, no twist, no ripple, no faint whisper will be overlooked. But even with all this, there are boundaries no lens can cross. Light from beyond our horizon will never reach us. Space itself expands faster than photons can travel. No detector can retrieve a signal that physics itself has locked away. This is the great limitation, that perhaps the multiverse, if it exists, will forever remain just beyond our grasp. And yet, there is a quiet defiance in the work, for science is not built only on certainty, but on the stubborn belief that the unknown can be brought into the light. Every new instrument, every mission, every model we dare to run, they are not simply machines. They are our fingers stretched into the dark, feeling for the pulse of something greater than ourselves. If one day, an unmistakable sign arrives, a distortion in the CMB, a gravitational shiver unlike any from known space, a particle slipping into another dimension, then the sky above will no longer be a boundary. It will be a window, and in that moment, humanity will stand knowing that our universe is not all there is. There is a certain humility in the thought that our universe is not the universe, but merely a universe. For centuries, humanity looked to the sky and believed it to be a singular, infinite stage, a singular reality in which every star, every law, every truth was written into the same script. But if the multiverse is real, that belief collapses into something stranger and more humbling than any ancient myth. The speed of light, the pull of gravity, the curvature of space-time itself, these are not divine absolutes written into the foundation of all reality. They are local customs rules that apply here, within this particular cosmic bubble, but perhaps nowhere else, somewhere beyond the reach of our telescopes. Another universe may hum to a different tune. Its speed of light could be slower. Its stars could burn in impossible colors. Its chemistry could forbid the existence of water or life, or anything resembling our familiar matter, and somewhere else still, there could be nothing at all, just a cold and endless vacuum. A cosmic silence so perfect it has never known the sound of a single atom colliding. This is the strange gift of the multiverse idea. It expands the imagination to a scale where possibility itself feels infinite. And yet, paradoxically, where meaning feels both fragile and eternal, because if there are countless universes, the fact of this one, the fact of us, becomes something extraordinary. Against a backdrop of infinite possibility, our existence becomes both inevitable and profoundly rare. Physicists debate the mathematics of such a reality. Some, like Andrei, Linde, see eternal inflation as a cosmic engine, a churning froth of universes bunning off into infinity. Others, like Max Tegmark, classify the multiverse into levels, each stranger than the last, from simple cosmic copies of our own space to entirely alien mathematical structures where the very idea of space may be meaningless and still. Others reject it altogether, arguing that without the possibility of proof, the multiverse risks becoming philosophy dressed in physics clothing. But beneath the equations and arguments, there is an older human impulse at work, the desire to know where we stand. In an infinite sea, what is a single drop? In an endless library, what is a single page? Perhaps somewhere in that library, there is a universe where the laws of physics align just enough for a civilization to rise, one so advanced they have not only imagined us, but found a way to watch us. Perhaps somewhere else, life has taken shape so far from our biology that we would not even recognize it as alive. Or perhaps the vast majority of universes are barren eternal monuments to silence, scattered among the few where life can bloom. This realization carries a quiet weight. We are used to thinking of truth as singular, as permanent. But if the multiverse is real, then truth itself is provincial, different from place to place, world to world. It would mean that our constants are not cosmic commandments, but local dialects of a much greater language. And yet, the search continues. For even if we never find proof, the act of looking becomes its own form of meaning. Perhaps we are not meant to grasp infinity, only to be moved by it, to live our brief lives as explorers standing at the edge of an immeasurable ocean, listening for the faintest sound of another shore. The cosmos, then, becomes an endless library. Each universe, a book, some filled with stories of life and light, others with nothing but blank pages. We, for now, are characters trapped within a single page of a single book, able to imagine others, but never to turn the binding. Still, we wonder, we dream, and in that dreaming, we reveal the most human truth of all, that even when confronted with infinity, we long to connect, to understand, to see beyond the walls of our own world. And so, the question lingers, carried not only by scientists, but by poets and dreamers alike. If other worlds exist, will we ever know them? Or are they meant to remain forever beyond our reach, existing not to be found, but to remind us that the page we inhabit, however small, is still worth reading?